Excuse me. So commercial utility interactive photovoltaic system. I don't know if you guys remember the one that we did about residential. I do have a couple of PowerPoint presentation slides. I'm going to go over them. Then I'm going to do some calculation, show you how to do some calculation based on the modules and so forth. Solar system. You guys are familiar with it. Just an overview. You have panels. You tie them with wire to an inverter. From the inverter, you dump them into the grid. Really, this is the kind of the big picture. So let me just draw the big picture. Very simple picture. You have a solar panel here, and you're tying it to an inverter, and from the inverter, you're tying it into the grid. This is your AC system, and this is and this part is your DC system. This is your DC system. So you took, this is my panel, solar panel, and from the solar panel, you generate a DC. I'll show you how we're going to calculate this. A DC, you invert, you can't tie DC to AC unless you want to see a big fat spark coming out. So you take AC, you generate DC for the most part, you convert it into AC by inverting it back into an AC, and you dump it into the grid so you can utilize it in different ways. That's really the whole photovoltaic system summarized. Cool? So let's go into a little bit into the details in a second. We'll go into the details. A couple of things that we need to achieve from this one. You need to understand the components that's associated with something called utility interactive inverter, utility interactive photovoltaic system, utility interactive photovoltaic system. There are three types of system that you guys can have. One is called utility interactive. It's basically directly connected, continuously connected to the grid, and you are shooting the power to the grid, selling to the grid directly. That's utility interactive. You also have a hybrid, a standalone, which is you live in the boony land up north in Minnesota, and you are isolated from the whole universe, and you want to have your solar system and run it. That's standalone, right? No grid, nothing, right? And the other one is a hybrid in between. We'll talk about these in a second, guys. The other thing is, so remember the word utility interactive. The most common one is the utility interactive, at least in the area, because then you can send power to Excel or receive power from Excel. We're going to talk about the functions of utility interactive inverters, the components, the functions, the National Electric Code requirements for the design and the installation. Again, design and installation of commercial interactive photovoltaic system. So what are they? What are the functions that they do? And what's the NEC code requirement for them? Cool? Can I have a thumbs up, Chad? Yep. Cool. Okay. So moving on into okay, again, interpret typical utility interactive solar photovoltaic single. The second thing is, guys, they have something called single line diagram. Remember the one line diagram that we drew? You guys are very familiar with the one line diagram. That's called one line diagram. The only difference is they add the solar system to it. Really, the one line diagram that you did with me, or the riser, it's exactly the same, except they added photovoltaic system to it. Okay, a couple of history stuff about this. Utility interactive inverter, guys, have been around for years, and Chris, you can help me here. They're talking about it was active with NASA and all those guys in the 60s. The whole idea of utilizing the Mother Nature sun, or the natural sun into utilizing electrical power is not a new concept. You know, used early in the 60s. In the NEC code book, up to my knowledge, I think it's a cycle 1984, NEC 1984 is when we introduced the NEC concept into the National Electric Code as an article. And as you know right now, this article is 690, the one that we'll be reviewing in a second. So, why the buzz these days, Ashley? Because we're becoming more environmentally friendly, aka tree huggers, like Chad always say. Independent of foreign oil and all these things that's coming around, it becomes more buzz. And Chris, you can agree or disagree with that one. I think designing things green is becoming more the trend of the industry, much more than it used to be. That's why it's becoming a big buzz now. So energy conservations and environmental concerns made a big deal for us. There are two articles that associated directly, guys, with the solar photovoltaic system. Number one is this article, which is solar photovoltaic system, tells you how to build the system. as in electrically how to wire it, how to protect it, how to disconnect it, how to so wire, disconnect, and protect. And then Article 705, since the photovoltaic system is another generating facility, every time you have two generating facilities in an area, you have to go to Article 705 because it has some regulations. How do you tie two? You have the grid and you have a power producing facility. Tying them together requires some marking and disconnecting and synchronizing that you have to do, and that's basically in Article 705. I will touch on 705, guys, when we do paralleling for next project. But think of it this way. Every time you have a generator that you need to tie to a grid or two sources of power tied together, you have to adhere to the rules of 705. And if you guys look at 705, it says interconnected electric power production sources. Interconnected, so you're paralleling sources. One major component, guys, is you can't tie them together if they're not in sync. You have to make sure that one of them is not driving the other as a motor, and marking and all this good stuff. So these are rules associated with the photovoltaic system. Any comments, any questions, guys, before to get into the detail, a little bit more details? Okay, how does the magic work? You guys are very familiar how this thing works. You have light. Here's my light. My light is called photons. These photons, when they hit a specially designed material, semiconductor material, which is mostly kind of diodes, the photons, the light, when it hits a specially semiconductor material called diodes, it created a DC voltage. That's the magic behind it. Specially designed material, mostly semiconductor diodes. Electrical current will be produced at the DC level. Electrical current will be produced. So then you got yourself an IDC and a VDC. You got a DC, and I'm not going to tell you guys, if you take an IDC and a VDC, what do you get out of an IV? You get power. That's exactly what we're after. So when these photons hit and get absorbed by a specialized combination of semiconductors, an electrical current is generated. That's how we capture Mother Nature's sun, or sun, into electrical current. Any question about this? How do they manufacture it and all this stuff? We'll leave it to the manufacturers. We take these panels that's specially designed to absorb these photons and convert them into a tiny, tiny current. We're not talking about 4,000 amps. We're talking about an amp, multiple amps, and so forth. Any question, guys, about this? Here's the material that they use commonly. Everything is silicon, guys, is semiconductors that they use, fabricated into wafers and infused with phosphorus gases. So they put these materials, fabricate them, build them, so they can generate current. What's the key point? Photons hitting this specially designed material, convert it into an I current with a voltage, multiply the current by the voltage. What do you get? Power. You get the power. Any question, guys, about the generation of the photovoltaic? How does the photovoltaic works? And you can generate small amount of voltages and small amount of current, but what you do, you group them, you series them, guys, and parallel them to get you a huge amount of power. That's the whole idea of series them and power them to get you a huge amount of power. Any comments, any question about how the whole magic behind it? How the whole magic behind it? So I'm just going to draw a little bit of two solar panels here, and I'm going to say positive, positive, negative, negative, and I'm going to tie these two. I'm going to tie these two, my friends, into, let's just say, I'm going to bring them from here and bring this one into here and tie it into here. So suppose that was, see, I put them in series, right? I put them in series. Suppose that was 5 volt and that was 5 volt. What do you think, guys, the output here would be? 10 volt. Remember how Mr. Ryman told you put two panels, each one of them is 5 volt by design. You put them in series, what happened to the total voltage? You get 10 volts. Okay, now suppose each one of these, then here's where you get the voltage. Suppose each one of these panels is carrying 1 amp. I'm just throwing 1 amp. If you put them in series, the amp, does the amp change when you put sources of power in series? Stays the same. So then continues to provide you with a 1 amp. So now take this, Ashley. I got myself a power source. Power equal 10 times 1 equal 10 watt. I have just generated 10 watts. Not a whole lot, but I've just generated 10 watts. Any question, guys, about the whole concept? It's like batteries. How do you put batteries in series and parallel? You series them to get higher voltage. When you parallel to them, you get higher amps. Okay, now take this. If I want another 10 volt, another watt, 10 watts. I want another 10 watts, right? Because 10 watts is not enough for me. You know what they do? The smarter than Chad. Take this. They come over here and they put another panel here. Here's 2 panels, right? Plus, minus, plus, minus. They bring the same thing. See how we repeat itself? Come over here and come over here. And we know what they do. They come and they tie the negative. Am I in the negative here? Where's the negative? Negative. Tie the negative to the negative and the positive to the positive. You see what we did? We have another 5 volt, another 5 volt. So another 10 volt system. Can I put 2 10 volt systems together in parallel? Yep, they have to be the same. By doing it this way, do you know what the outcome is? You double the voltage. Now you multiply this by 2. So what do you get? How much current you get? The current here would be 2 amps now. 2 times 10 is what? 20 watt. You got yourself 20 watt. If you understand this concept, that's exactly what they do for the solar system, guys. They keep adding panels until they hit the voltage that they want, 600 volt, 400 volt, and then we got the voltage. Now if we need more current, they add another string. They call this is one string, another string. So they add another string to get more power. Okay? Any question, guys, about adding panels, series them together to get the voltage, and then parallel the strings together to get the amps, more amps? Ultimately, what are you getting? More power, more power. Ultimately, you're getting more power. Okay. So the bottom line, guys, when we deal with photovoltaic system is the photovoltaic modules, these panels that we use, produces direct current when exposed to the sun. You have the specially designed modules that has semiconducting material in there. You expose it to the sun, you generated DC current. You generated DC current. And then, now we got the DC current, right? Now then we put an inverter. Oh, I didn't show you guys. If we go back here, do you remember that power that we did here? That 20 watt power here? If I want him 20 watt AC, so what do? They put an inverter here that invert the DC into AC, right? Like, remember how the AC we invert with diodes, with electronic equipment, we cut the DC voltage, invert it back into AC. And now when we capture AC at the right frequency and the right voltage, we can utilize it commercially. You can utilize it commercially. Okay, so we generated DC from the sun. Then we have converter, converts the DC, that's the key point, into AC. That's the key point is, take the DC into AC with utility and synchronize it with the utility. It's not just enough to convert it, you need to synchronize it. Take this. Here's my generated signal. Here's my generated DC signal here. Here's my, let's just say 400 volt. Okay. Now I can't dump this one into the grid. This is the DC. Now what happened is when I invert it, it converts it back into a nice sinusoidal wave. I'm showing just one wave. And that wave, let's just say that wave was 240 volt top, 240 volt RMS. Let's just say an RMS. 240 RMS at 60 hertz. Now, if I capture it 240 RMS at 60 hertz, I have just got myself into a photovoltaic system. Any question, guys, how the output of the modules is DC? You dump the DC across the converter, it converts it into AC, and it synchronizes it. So if the AC, now we have the AC, but the utility has an AC, this one, and I have another AC. What they do, guys, they convert it. Here's my utility. I take my my grid voltage and match it. That's what's synchronizing it. Match it to the grid, then lock it with the grid. Now me and the grid are running at the same voltage, same frequency. If it's an interactive, and we're talking about the interactive. Now this is if you want to sell it to the grid. Well, what if you want to store it so you can use it when the sun comes down? So actually what we have then, we have battery system that you can store. Right now the commercially available system is batteries to store energy. So you have a bank of batteries and you dump all this energy into the batteries. When the batteries are full, you're done. You can't store more. Any question, guys, about this system? So we have modules that generate DC power. Then we convert it through the inverter into AC power. We synchronize it with the grid and we dump it to the grid. Any question? Did I put you to sleep, guys? What? Does that make sense? Chris, I know you researched it. Okay, so that's your... Now let's look at this picture. This is one of the most important pictures in the NEC code book that you guys are going to have. Very important things. My point is, when you deal with the systems, you have to identify a few things. Here's my modules. Can you guys see where the modules? My modules are right here. I'm going to take one of these modules. Here's my modules. I can series multiple modules to make a panel. You can see here's my modules. I'm serying multiple modules to have a panel. Here's 1, 2, 3, and I went through the fuse and I went through the diode and I jumped in here. Okay, and I have another. So this panel, imagine that this panel by design, all of it, now these two make a panel, right? All these modules in series, like I showed, make a panel. Well, let's say this panel was 50 volt DC, 50 volt DC, right? Any question about that? It's by design, it's giving me one panel, give me 50 volt DC, right? At a current of, let's just say at a current of 1 amp, 1 amp DC. So I am generating, here's my amp, 1 amp, let's use the current. So here's my voltage, V DC, and I DC, 1 amp, okay? Now the power for this string, what's the DC power for this string, guys? 50 volt, right? 1 times 50 equal 50 watt. This one that I highlighted have generated 50 watts to the system, DC. 50 watts DC. Any question, guys, about that? This string have generated, call it string, 50 watt DC. 50 watt DC. Okay, now I want you guys to look at the other one. So I have the other system is also, here's another 50 here. Can you guys see that? Another 50. It's coming from here. 50 volt and another 50 volt. Can I tie the 350s together in parallel? Since they are the same voltage, we're tying them together at the end, okay? Now the outcome right here, if this is going to give me 1 amp, I have 1 amp here, and I have 1 amp here. These are identical. What do you think the amp here is going to be? They're all in series. 1, 1, 1. What happened when you put the currents? When you put the current in, when you parallel the current, they add up, right? So this will give you 3 amps at 50 volt for a total of power DC of 3 times 50 equal what? 150 watt. Done.
What's drawing current?
Load.
Okay, what's the load?
You're going to tie the load right here. This will be going all the way to the inverter. We're not showing it. This will, from the output, photovoltaic output circuit, will be tied to an inverter, and the inverter is tied to a load. You put a load, you start pulling the current.
Load supplied by the power company.
Yes, that's your house. That's the building.
I thought we were supplying Excel Energy.
Yeah. Or, yeah, you can. The power can go to your house if you need it, and the extra will go to Excel Energy. We'll show you the interface here. Any question, guys, how to generate? This is your generator. Yes, sir. There is no batteries yet. This is just a generator. We're generating power. We're not storing it. This is the generating mechanism. It's coming.
How does it run at night?
Well, hold your horse. It's coming. It's the next slide will be it. This is just generating the power. This is just generating the power. Can I get you guys to understand that this is called photovoltaic sources? Can you see the diodes? Anybody knows why the diode is? The diode is because you don't want this string here to feed this. If there's a short circuit here, you don't want one panel to feed the other, or one set of panels to feed the others into a short circuit. So I have the solar cells, I have the modules that make panels. All of them together, they're made array. My array of photovoltaic system. You can have as many arrays as you want, but that's my generator. This is my generating plant. Any question, guys, about how to generate? When you deal with the code, guys, very important things to understand. Can you guys see the fuses here? You are required sometimes to have a fuses, and sometimes depends the fuse to fuse them. I have the block diodes because I want to isolate these systems. I don't want them to feed each other. And then I combine them, and the combiner is called photovoltaic output circuit. Photovoltaic output circuit. Photovoltaic output circuit. Any question about that? How does it make sense? How to generate with these? The most important thing, guys, is how we series these to get you a 50 volt. What's 50 divided by 3? Just 50 divided by 3 equal, say, let's just say 17 volts. Each one of these is 17, 17, 17. When you add them up, we'll add up plus or minus, we'll add up, say, to 50. I know it's approximated, but add up to 50. So we series them, we got a voltage, then we parallel them to get more current, to get you more power. Any question? The key point, guys, what they do is, first, you have to capture the voltage. You can do up to 600 volt in residential and higher in other than residential. So when you get 600 volt, you keep series the panels to get 600 volt, then you need more power. What do? You keep adding one more string. So here's one string like this, add another, and a third, and a fourth, and a fifth, and so forth. What you're looking at right now is a power plant. This is a power generator, basically. A solar power generator. Any question? William, does it make sense? Rob, my friend? Okay, now we'll get back to this, how to size it and disconnect it and all this stuff. And I'm going to get back, Dustin, to your question. There are two ways there are two inverters, guys. One of them is AC inverter, one is DC. This one here, the one that you're looking here is a DC. This is DC system. The smarter than Chad, you know what they do? They have a panel that has actually an AC inverter on them. So they have AC module system. Each one of them has an AC module on it, and they convert at the AC level. So let me just say this was 50 volt AC. Each one of these, 1, 2, 3, right? And each one of them is taking 1 amp AC. So the total here will be 3 amps AC. And the voltage is 50. So the power AC equal 3 times 50 equal 150 volt amp AC. See what they do? They have two types of inverters. You can generate at the DC level, or you can generate at the AC level. These panels, Chris, they have the inverter built into them, microinverters. They have microinverters built into the panel. Any question? Any question, guys, about the whole system? Okay, moving on. Here's Dustin. Here's what you were asking me about. Now, after we capture them, here's we capture the panels here. Here's all my panels, right? And here's all my panels. We capture them here. Here's all my panels, right? The one that we captured. And here's my 1 amp, 1 amp, 1 amp. Remember the 1 ampere? This is 3 amps. Now, the voltage, we decided our voltage was 50 here, 50 volt. So can you guys see that? After that, you bring it to where? To the inverter. You bring it to the inverter. You capture what they call it photovoltaic output circuit, and you bring it to the inverter. And what do you think the inverter does? This is called inverter output circuit, and the inverter, my friends, will bring it into your panel. will bring it directly into your panel, AC panel. Will bring it directly into your AC panel. Can you guys see the big picture? I have my panels generating 1 amp, 50 volt. I paralleled them. I got 3 volt at 50 amp. I inverted it back. When I invert, let me just do this example. Let's just say we inverted it at 240 volt. I inverted it back at 240, and let's just say whatever that would be an amp. So we inverted at 240. At 240 with whatever amps that we can get. What 240 at say 0.75 amps. Any question, guys, how the system is put together? We generated the amps at the right the voltage that we want, bring it to the inverter, invert it back, dump it into the grid. This is what we call it interactive, the most common one. Now let's go to the hybrid. Let's go to this one, the standalone. Then there's another system. This is if you want to dump it to the grid. The standalone system, look what they do, guys. They bring the same system from here, same system that you brought here, into system actually from here. See, right here. The same system, the same wires. Can you guys see that? We bring it to a charger. Now I need a charger. The charger will charge energy storage, which is AKA batteries. This is my battery system. So I have a charger. I take the DC. From the charger, I charge the batteries. And I can also take a DC load. If I want to run something at 24 volt light, I can run a light at 24 volt or whatever voltage I'm running, DC, okay? And I can also have my inverter invert back into 240/120 AC. Invert into AC. So can you guys see the flow of the power? The power comes in into the charger. Some of the power will go charge the batteries. Others will go feed the load. And part of the batteries goes into the inverter, out of the inverter into my other lights and systems, which is AC. So I can get 2 types of loads in the system. Because I live in a boony land, I can get 2 loads. I can get AC or DC. I can get a load that AC or a load that DC. Any question? So that's the standalone system, right? I have interactive with the grid. There is no grid here. Can you guys see any grid here? No grid. Interactive, no grid. The in-between, you can have a hybrid. That baby here, they call it a hybrid. Look what the hybrid is. I can have my solar. This is coming from my solar. And I can have wind. Can you guys see wind? Bring the wind in here. I have generator. Bring the generator in here. Can you see how many sources? I have 3-4 sources coming into this system. And I can have an energy storage system, batteries, and a charger or charge controller. Multiple systems basically coming with the solar, with a battery. And out of the whole deal, I can capture it as DC load. I can go feed DC load, or I can invert it back into an inverter. I can invert it back into an inverter output circuit and feed all my loads at AC level.
And the smaller inverter, 3,000 watts, do the same thing.
3,000 watts? Yeah, you have to buy an inverter that matches your load. Yeah, you can have 5,000, 3,000. This inverter? Yes. You're taking from the inverter power at the AC to feed the load.
No, what I'm saying is that the portable inverter, the 3,000 watts inverter, which 3,000 watt inverter? They sell some inverters in town. Understand?
As long as, guys, these are specialized. This one is interactive. These inverters, you can almost, as long as you can capture, the inverter has 2 things. You have to capture the DC voltage and current, has to be rated for the DC voltage and current on this side, and the AC voltage and current on the other side. If you can match the AC voltage and current here and here, match it to your power system here and your generation system here, you can use any inverter. I don't know what this 3,000 I'm sure it's if it's 3000, if it's the right voltage and the right voltage, then yes, you can tie it to this side. If it's and now the right voltage in the DC, there's AC side of the inverter, and on the inverter, if the right AC, then you can capture it, then you can use it. Any I almost, yeah, I hate to say any inverter, but as long as you match the voltage of the inverter to your generated voltage, and then to your load voltage and frequency, you can use it. If it's interactive, it has a lot of requirements for interactive ones because you're tying to the grid. These guys are isolated, hybrid system. The isolated ones, yeah, you're not tying to the grid, yes. But I would use an inverter. It will work. I would use an inverter that's rated for photovoltaic system, though. I wouldn't miss and match. I mean, when you buy the system, guys, they buy the inverter that matches the system with it. So, any question, guys, about this system? The most common right now in a commercial is the interactive here. That's the reason why we have it. Interactive, because you can sell to Excel energy and reduce your consumption of power. Yeah, the
inverters for this are very specialized because the voltage varies. There's a huge fluctuation in voltage due to the sunlight out and when the sun is available and the ambient temperature.
Absolutely.
So standard inverters that are made to take battery power to electricity
might not cut it.
Yeah, they're not going to cut the mustard because they're set. You know, if the battery is between 14 volts, but instead of a 12-volt system, between 14 and 10 is going to produce something that will not work otherwise. This variation is much better.
Thank you, Chris. What I would say is it's a complete system. When you buy the panels, you buy the inverter that goes with them. But doesn't mean that any inverter doesn't work. But to work, guys, things work. But does it work properly, safely, and efficiently? That's what you're looking for. To make the inverter work properly, safely, efficiently, you need to buy an inverter rated with your system. Done. Because there's a lot of inverters that you can do. Okay. Photovoltaic system, guys, the components of the system, as you can see, the first thing was the module. Remember that module deal? This is what they call it, the module, right here. See that little module, the 17, when you put them together to make a panel, that's called a module. If you go to the module, this is they call it the basic building block of the system. That's where we generate the voltage. That's it. This is where the rubber meets the road, as we say. And then individual photovoltaic semiconductors, it's made out of semiconductor cells that generate electricity connected together as a unit. Efficiency and size and cost differ, from manufacturer to another. I'm not going to get into all this, which one is more efficient. You can buy anything you want. All of them have to meet certain standards. Some of them are more efficient than others. Produced with wire leads. Most of them, guys, come here. They come with some type of wire leads for connection to other components of the system. What they do with these modules, Aladibo, my friend, here's module 1. Here's module 1, say, and I'm going to make these two modules a panel. What they do is they have a manufacturer produced cable with them. We can plug this module into this module by plugging it. And these plugs are load interrupters, so you can unplug any of these panels. Usually the panels, you put 4 modules to make a panel, and then they're all plugged into each other, and you can unplug one of them for service. Unplug it safely, and work on them. So they are produced with some wire leads to safely disconnect them. So these are the modules. You put the modules, which is the panels, together, guys. So collection of modules together. We'll combine them to create some array. The array is a bunch of modules put together to create a generating unit, a generator, like we did here. Here's what you're looking at right here, back. Do you guys see that? All this together, all these 9 modules in 3 panels are together creating what they call it array, or a generating unit. If I need more power, I can have another array, and a third array, and a fourth array, and so forth. Okay, so here's my my array. Okay, so we got our arrays, guys. Then we have a combiner boxes. Series connected strings of modules are connected in parallel to the string. Can you guys see the combiner box here? They call it combiner box. You connect the strings in series. You put your strings that's connected in series into parallel to connect to create the power. Here, can you guys see right here? This is where your combiner box is going to be sitting right in here. That's my combiner box. What does a combiner box mean? You bring all these strings and you tie them together through diodes and or fuses. So if one of these strings, so-called string, which is multiple panels together, one of them shorted on you, you want to be able to isolate that string, work on it. So they have to have a box. You see, look at that box. It's called combiner box. Some of them have fuses recommended. You might not need a fuses, depending upon the size. We are showing fuses. Can you guys see how we're showing fuses? So they have diodes and fuses inside them to isolate the system. That's what they call a combiner. Okay, disconnects. You have to provide a disconnect. We'll talk about disconnects, guys, based on NEC code book. Provide requirement for installation of disconnects. Disconnects, you have to provide a disconnect on every side of the inverter. You need to be able to isolate the inverter on the DC side and on the AC side. So if this is my inverter, I need to be able to disconnect the inverter on this side, which is AC side, and I need to also be able to disconnect the inverter on the DC side, which is, this is my DC side where the panels are located, where all my panels are located. Can you guys see that? Think of it as an inverter have to have two disconnects. A lot of inverters have a disconnect inside the inverter for the DC, outside the inverter for the AC. Inside the inverter for the DC, outside the inverter for an AC. Why do we have a disconnect? To completely isolate the system. Completely isolate the system. And also, actually, when you come over here and you tie it to the grid, right? This is where I'm going to be tying to the grid. You need another disconnect right here. Disconnect where I tie, this is my panel. This is my service coming from Excel Energy. Utility. I have the utility here going to the panel. I tied at the line side of the disconnect. I need a disconnect right next to the utility as you tie it to the utility. That disconnect to disconnect the whole system from the grid if it's interactive. Can you guys see the major disconnect that you need? To this disconnect and this disconnect, the utility, the AC inverter disconnect, and the utility disconnect could be the same disconnect depending where they're located. The DC disconnect most likely would be part of the inverter, part of your inverter. Okay, so that's my disconnect. The second thing that you need to know is the inverter, guys. So we take, what does the inverter do? Take AC, convert it to DC. That's the major job of an inverter. Take a generated voltage that looks something like this. Let's say 600 volt DC, and convert it into a beautiful, signal that looks something like this. And this voltage RMS value is 600 volt AC. I took 600 volt DC and convert it into a 600 volt AC system. Or you can convert it into 208 120 volt 3-phase AC system. Any question, guys, what the inverter does? Take a DC, chop it down into little pieces with frequency, and oh, by the way, frequency 60 hertz. You need to synchronize it with the frequency they use, 50-50, 60-60, okay? Into alternating current. And the key point is, this is the key point for interactive ones. Can you guys see the word synchronize? Next quarter, we're going to have generators. We're going to synchronize generators with the grid. You need to be able to synchronize the voltage with the grid. So here's a little key component for this particular one, guys. Suppose that this is my voltage coming from the inverter voltage, and suppose that my utility voltage is something like this. Okay, so I need to be able to, this is my utility. So I need to be able to synchronize them, guys. Grab them together and match them. There's two of them. Grab them together and match my voltage with the grid so they can lock with the grid. Otherwise, You know what happens if you don't lock them together? Like for generators, it's like driving your car at 80 miles an hour and put your gear in reverse, if you can, or if you put it in lower gear, if you have a gear car. What happened to your gear? It's gonna bust. So that's equivalent to connecting two systems together when they're not in sync. Okay, so I can't emphasize the word synchronization. Any question, guys? I know this is a kind of an advanced topic for some of you. It's the buzz now. A lot of companies that might come to your company when you work, they want to put a solar photovoltaic system at the top of the building. Very important to understand it. If you know this, that's an edge that you have above somebody who's sitting next to you who doesn't know it. Okay. Inverter. If you have utility interactive inverter, guys, back to my inverter. If it's utility interactive inverter, you need to have, it has to adhere to a rule under UL1741 rule. Very simple rule. UL147 rule. You need to be able, this rule says, they call it anti-islanding. That inverter has to be able to do a function called anti-islanding. If you're tying with the grid, what happened if a tornado come in Minnesota and hit the transmission line and you lost power? What happened if you lost power and you're tied to the grid with the solar? Now the whole building, 4,000 amp switch gear, 4,000 amp load at 480 is tied directly to the solar system that's only supposed to provide a 1,000 amp, right? The 1,000 amp. So first you could burn your equipment, but there's a protection for this. The second thing, now you lost the power. Now you want to be, if you lost the power, you want to be able to turn off the utility. If the power is lost, they want you to have a function to turn off your system because you're feeding into Excel, guys. So here's my power here. I'm going to utility here, and this is to my load, and this is my system. I'm bringing 2,000 amp here, 2,000 amp. Most of it, let's just say 1,000 is going to my building, and 1,000 I'm feeding it to Excel, right? I'm generating 2,000 amps. I'm giving Excel 1,000, and I'm loading 1,000 because my load is, I don't need the other 1,000. Cool? Now what happens if Excel shuts down here for maintenance, and you're still pumping power into their grid? You could kill a maintenance guy. Well, they have a lot of protection on their side too. They don't want you to feed back into their system when their system is down. Long story short, anti-islanding, they want you to, if you sense the power is down and you have an interactive, they want you to shut down your system or isolate your system from them. Either you shut it down or you isolate your system from them. So you have to have some means of isolating your system from them. Okay, so that's number one. And you need to also have the ground fault protection on your DC side. They want you, the inverter have to have the ability to sense that there's a ground fault on the positive side. Remember, ground fault on a DC is going to be on the positive. The negative will be grounded. The positive you have, what happens if you go to the positive and you tie it to the same ground? Short ground fault. You want to be able to sense that there's a ground fault and open the inverter up on the existence of ground fault. So that's what they call it. First, you lose power, isolate your system from the grid, either by shutting down your inverter or by diverging the power away from the grid. And the second one, you have to have a ground fault protection. So these are coming from your listing. Also, the NEC code book, believe it or not, they have an arc fault circuit interrupter requirement for the DC, guys. If your system is above 80 volt, if you have any system above 80 volt, they require you to have an arc fault circuit interrupter system. So they want you to be able to see when that positive start arcing to the frame of the panel and creating fire. Remember, we have 600 volt DC. So start arcing, you can create a fire. If it arcs, the inverter should be able to sense that there's an arc in the system and isolate the inverter, isolate the whole system. Any questions, guys, about this requirement? Almost everything that you buy interactive has to meet these rules. So ground fault protection and arc fault protection. Okay, the couple of other things, guys, that we have here is the site. When you put your site or plot plan, when you design a system like this, obviously you have to have the site plan like we did. Instead of showing, in ours we showed the fixture, the parking lot fixture. We have to show the location of all these solar systems. So you have to have, so here's my site, and I'm going to go plant all my modules this way. Here's string 1, here's string 2, or array 1, array 2, and this is the plant I'm going to be doing. So you have to have some type of a site or plot plan, PVC component and existing electrical systems, and then you're going to show how they're going to be, each one of them is going to have an inverter here. These are all tied together, right? And the output of the inverter, I'm going to go take them to my grid. Bam, bam, bam. I'm going to take this one into my 4,000 amp, 480 volt, 3-phase, 60 hertz system. So I showed all my panels. I'm generating here at 600 volt DC. I inverted them back into a 480, tied them all together, and brought them all the way to my system. These are major systems, guys. Each one of this is array 1, array 1, array 2, and array 3. It has its own inverter. Inverted the power, tie them together, and dump them all the way. Well, usually grab them all with each inverter output all the way, and you tie them to your grid. You don't have to have 3. You could have 1 or more than 1. Then site one line diagram. I think we have one here. Site one line diagram, guys. Here's a very good example of site one line diagram. I want you guys to look at this. Here's my utility. Can you guys see the utility right here? I'm bringing the power, the positive. Can you guys see with the positive and the negative? I'm bringing here's my power coming from all these modules, negative, and here's my disconnect for the inverter. Can you guys see my disconnect, inverter disconnect, my fuse, if any, and I brought them into the inverter. Can you see this is my DC? In the inverter side, I'm inverting at 240 volt. I need a DC disconnect. Here's my disconnect. Can you guys see the disconnect? You have to disconnect the inverter. Disconnect 1, disconnect 2 on the both sides of the inverter. Then you have to have a disconnect for the utility. This is the one that's going to go disconnect you from the utility. And then, of course, you have to dump it into your panel. So you have to have an overcapacity device. Now, Chris, 1, 2, 3 could be only 1, depending how you arrange them. These 3 could be 1. Okay. And then, now we're dumping the power at the grid. You need to create a grounding electrode system here. This is for your grid. Also, you have to have a grounding electrode system for your inverter. You have to ground your inverter right here, bond and ground your inverter, bring it to the ground, and also you have to tie the 2 grounding electrode systems together. Can you guys see that? And your panels most likely will be number 6 copper CU, coming all the way for grounding all these panels on the roof or somewhere else and going to Mother Earth, tying them to Mother Earth. Any question, guys, about this? All my panels, take number 6, ground all the panels. You see a picture of it inside. Take them to the grounding electrode conductor. Here's my positive and my negative coming into the panel, into the inverter. And the inverter can have multiple sources coming to it, or there could be a combiner that combine all of them here and dump it to the inverter. Can I, guys, get you to understand the following? The disconnects, see the disconnects where the disconnects are located for all these systems on each side of the inverter, 1 for the utility, 2, and the grounding electrode system for the utility as well as the system for the inverter. You have to ground your negative here. The negative will be grounded right at the inverter. Bond the negative to the ground at the inverter. And then you have to have a bonding conductor that goes all the way to the panels and down to Mother Earth. Any question? Any question, guys, about that? So that's what they call it, one-line diagram. Now I'm showing only one panel. You can have 10 strings like this, tie them in a combiner box, and bring them to the inverter. Bring them to the inverter. Okay, calculation. We'll talk. How about if we take a break? Please take a 5 minutes break, and we'll talk about calculation. Almost done, guys.
problems yesterday. Well, you are not getting my message.
I want to show is all right, let me see here. When we size for the photovoltaic system, they use very important concept. They call it open voltage. Open voltage. So the voltage that they use is called the open voltage for the panel. Say if this 50 voltage, like you said, Chris, this 50 volt is if you grab the positive and the negative and open them, you don't connect them to the load and measure. That's exactly what you get. Number one. So the maximum DC, and then the current that they use is I short circuit for the modules. I short circuit, say 5 amps. This means if I grab the positive, guys, and the negative, I shorted them together, that's how much current I'm going to do for safety. So if you have a module, very important, if I have a module, and this is positive, negative for the module, and I grab my negative here, terminal, and I grab my positive terminal, this is the voltage, V open voltage, open circuit. We call it open circuit. I'm sorry. V open circuit, V open circuit, V open circuit, and the current right here is actually as if you shunted these two together. That's the current that they want you to use. We're not going to show it here. So that's I short circuit. That's what we use for sizing. Always we use these two voltages. When we size conductors, what they do for sizing conductors, I'll talk about these one in a second as we go. This is for the DC. For the AC, you take the current coming out of the inverter and you multiply it by 1.25 because it's continuous load, and you size over protection device and the conductor. So 1.25 times I AC inverter. The inverter current that's coming out multiplied by 1.25, and you're good to go. You have to do some correction for ambiguity, guys. If you're on a commercial garage, because of the sun is coming and hitting, there will be some correction for the conductors that you have to pay attention to. Okay, so we'll talk about this one in a second. Modular grounding, installing of combined box, large equipment, wiring, grounding electrodes. All these guys are concepts that you have to be, when you install them, you have to pay a lot of attention to mounting the arrays to get the most efficient part of the sun, obviously. Grounding the modules most likely would be a number 6 CU copper conductor. Combining box, you have to have a combining box that here's my combining box, and here's all my strings coming in, and we can fuse them and diode them, and from this side they're coming out and going to the inverter. Large equipment, wiring systems that we're going to be using. There's a couple of wiring methods that we use that listed in the NEC code book that we use. THH here, THWN. THWN is one of them that you can use for AC or DC. USE2, USE-2. These are wiring methods on the DC or the AC side. On the DC or the AC side. So these are a few things that you have to keep in mind before grounding. We'll talk about grounding electrode conductor, guys. We'll talk about sizing it in a second here. Size grounding electrode conductor. And there's a couple of signs. Utility point of connection. There's two connections. I'm going to show you how you can connect with the utility. Wherever you go, I guess.
You have a hard bargain.
Anybody else there? When you connect with the utility, you have to put a label and a sign and mark the equipment that this is. You have to mark your equipment that this is a source of power coming from the solar system. There's some signs and equipment that you have to do. Okay, connecting with the utility. Speaking of the devil, this is how you connect with the utility in an interactive system, guys. Chris, this is exactly what you were saying. Here's my utility transformer, and this is my transmission line that's coming to my building. Right here, and this is 13,800 volt, and here's my neighbor's building coming in here, building number 2 on the transmission line. And what I do is here's my building. I feed my building, and can you guys see where they connect right in here? On the line side of a disconnect means I have to have a fuse disconnect, mark it, label it as a fuse disconnect that's coming from the photovoltaic system. This is my interactive generator. And the power, this meter has to be bi-directional meter. because now the power is going one this way or the other way, bi-directional meter. It has to go through the utility transformer that I have here and tie into the grid, so I can feed my neighbor with whatever power I have. If you have this limit, if you have this system, then the limitation, the only limitation you have is how much your utility line can handle. So let's just put numbers here. Let's suppose that this was 2000 amp, 480 volt, three phase obviously, and I'm going to have my fuse disconnect system here as rated also. Let me say I'm going to generate a 2000 amp. 2000 amp, the same thing, 480 volt, three phase. So now if my building is consuming 2000 amp, all the stuff that I generated will be consumed by my building. At one time, because I sent my employees home, we're not working, we're low, so my load in my building went down to 1000 amps, right? But I'm still generating 2000 amps. The other 2000 amps will go right into my neighbor. So my others will go right through here, through the grid, and tie into my neighbor. And I'm giving my neighbor here a 2000 amp, 480 volt, three phase worth of chunk of power. And I am being accredited for it. And I'm generating power and sending it to the grid. That's the utility interactive system. If you, 1000 amp. See, I'm consuming 1000 amp right now. And the other 1000 amp is going to go, so it's going to have 1000 amp going this direction, 1000 amp coming this direction, because my load is low now. I know my system is rated for 2000, but I'm not using the full 2000. That's it. That's the best way of connecting your photovoltaic system. You have to mark the disconnect, guys. If you have, this is where your inverter has to isolate yourself from the grid if the grid is down, because then now you're feeding the grid with power, and you could kill electricians or burn your system. It will trip, but you don't want you to feed back into the grid if the grid is down. Any question? So can you see there's no limitation on the amount of power that I can generate here? No limitation on the amount of power. Okay, well look.
Limitation. You can't generate more than otherwise you'll burn your.
Thank you. No limitation other than what your service entrance conductor can handle. Service entrance conductors, which they'll be rated for the transformer too, or what the utilities allow you to do. The utilities also can set their meter to allow you only to shoot their way at 20% of what you can generate, or 30%. So there's a lot of issues involved here. Okay, but no code restriction on how much you can generate. Any questions about this photovoltaic system? That's the best way to tie your photovoltaic system. Okay, after you build the whole system, you need to commissioning. They call it commissioning. Construct is complete the process of initial startup. You have to, because it's a system, guys, that you have to do some startups for the system and commissioning. Commissioning, as you troubleshoot the system, make sure it works the way it is, tweak it, adjust it, and so forth. For instance, okay, energized, you have to inspect the whole system. There's a whole things that you need to do, guys. Inspect it. The system is operable. You have to do some calibration for your system to attain the maximum performance of your system, because you might have to readjust your inverter, or I don't know, readjust. I guess you hope you're not going to readjust your array. So there's certain things that you have to do commissioning and testing it. Typical for a major system. And that's basically it in terms of the system that I want to go over. There's a couple of pictures I would like to go over, guys, right here with you. So we went over this system. We went over this. The only thing I want to say about grounding and bonding for photovoltaic system, when we ground, and we will talk about this one, guys. When we ground the grounding electrode conductor, we go to 250.66. When we ground the system for photovoltaic system, for the most part, you're going to go looking at 250.166. 250.166 for the grounding electrode conductor. And that will allow you to size the grounding electrode conductor based on the largest DC wire that you're bringing to the inverter. Any question guys about this? Any question? Let me just tell you how they size fuses right from this, probably the same. Let's just say, take this. Let's say, what is it? 424 PVC modules. This is 28 volt PVC modules. Each one of them is 28. Can you guys give me the voltage, the open voltage here? This is V open voltage. V equal 4 times 28. What's V times 4 times 28, Alaripo? 4 times 28. Anybody has a calculator? 108, thank you. 108. We have somebody who is not awake. DC. This is my DC. So my system is 128 DC. Let me tell you how they do, guys. If the current that's coming out of this system right here is 5 amps, 5 amps, the way they size the conductor size, you know what they do? For conductor size, they take 1.25 times 1.25 weird times 5 amps. Can you guys do this? This is how we size it. The first 1.25 because to accommodate for the short circuit. The second 1.25 to accommodate for continuous load. The first 1.25 to accommodate for a short circuit because the I that we're using is the I short circuit. Okay, what would that be? How much? 112? Oops, now you see you misled me here. 112? So I have 2 volts. Okay, what's 5 times 1.25 times 1.25? Come on, guys. Where's the ones who's gonna get A's? 1.25 times 1.25 times 5 equal. Oops. 1.25 times 1.25 times 5. You have 7.8. I have 7.8 amps. Now, Phil, my friend, now you're going to go size your conductors based on 7.8, and your fuse is going to be sized based on 7.8. Obviously, you can't find a fuse, so this will be the size of my conductor. In this case, it's going to be number size of my conductor here is going to be number 14 minimum, and the size of my overcome protection device is going to be number 10 amps. Number 10 amps. I sized my overcome protection device right here and my conductor right here. Can you guys see that? My overcome protection device and my conductor for the inverter input. For the inverter input. Cool? See how easy that is? The second thing is the inverter output here. The output of the inverter. Let's just say, I don't know, let's just say we're inverting at so another 5 amps AC. Okay? So you take this 5 amps AC, guys. You take 5 amps multiplied by 1.25. What would that give you? 5 amps, 1.25 times 5 equal 6.25 amps. And this will get you number 14 and an overcome protection device of 10 amps. Again, these will be completely different, guys, when you add more systems to it, but the process is the same. If that was 100 amp here, it would be the same. If that was 20 amps here, the same process. Any question about sizing the AC conductors and the DC conductors on both sides of the inverter? Very easy. The only thing you have to remember is these two multipliers. One is for continuous load and one is for short circuit. To accommodate for short circuit. On the DC side. On the AC side, only one multiplier. Any question? So that's really the key point in of the sizing business here. Okay, now there are 2 ways of connecting. I told you guys this last year too. This is poor man's way of connecting to the grid. If you do it this way, then you're limited to only 20% of the rating of the system. So if you tie on the load side like this, then this overcome protection device here is limited to, you can't add more than 20% of what the system here. Say suppose I have 100, I have 200 amp main, then this guy has to add only the size. This have to be 200 multiplied by 0.2. 20% of the 200 is what? 20% of the 200. 200 multiplied by 0.2. I should know that one at least. 40 amps. So this cannot be more than 40 amps, and you have to put it at the end of the panel. If you do it, if you tie, this is how they do it in residential. A lot of residential stuff where you don't want to, you tie just a small load and you tie it as a load. Can you see this circuit breaker here? You're limited to only 20%. You can only add 20% to your panel. You can only add to the size of the panel. Your panel is 200 amp. You can only add 20% of the 200 amp, 40 amps. That's if you do it this way. Okay? Same rules. Interactive. Smaller system do it this way. If you do it this way, I hate to say unlimited, but there's the only limitation is how much Excel or the utilities allowing you to pump back into them, and what's the capability of your service conductor. No limitation, no code limitation. This is the only limitation here. Limitation of service entrance conductors and utility regulation. How many T's do I have in the utility here? And utility regulation they're going to be adhering to. So that's no limitation, like 20% of how much you can generate and dump into this system. Pictures of a couple of photovoltaic system, guys, all these panels. This is my favorite. This is the combiner box. Can you guys see all these? All these stuff that you can see inside here, these are where you can put your diodes and you can put also your fuses. So all these, every one of these is coming from a combiner. It's combining them, combining all these wires coming from here into, can you guys see it, into, tying them together with the rubber diode and coming out and going to the inverter. And then over here you can have all my diodes and stuff, all the diode stuff and all the fuses and all my fuses, if any. Can you see, these are what you're looking, diodes and fuses, combine them together and sending them down here into the inverter. For every array that you've done. Okay. I don't know if you can see, guys, can you guys see how that big black conductor and big white conductor here, that's your positive, negative, black, positive, negative, white, and going all the way down to the inverter, like summing them all up. Okay, here's an inverter. This is an inverter disconnects your inverter. You're bringing the array over here to the inverter disconnect, and you're taking it down into your grid. Your grid. Power coming out of your solar system to tie to the grid. I want to bring to your attention, guys, right here. Can you guys see that here? Anybody can see it? And you have the same picture. This is your grounding conductor. That could be number 6 CU copper. That tying and grounding all these panels and structure together and tying it to the grounding electrode system. Okay, now when you do the voltage, believe it or not, in Minnesota, guys, the lower the temperature, which is kind of opposite to what we think, the lower the temperature, the higher the voltage generated in a photovoltaic system. Take this. If I have a photovoltaic panel, and here's my positive, negative, and my open voltage for this baby is 50 volt of this panel. This is solar panel, okay? And I need to put it in Minnesota, and the ambient temperature could be in our great state of Minnesota. Ambient temperature, we could land probably easily in this area here at one time, right? Easily, minus 24 to 25 in the great state of Minnesota, right? Not all that in the winter, we can land on this. So look what happened. If you land it here, then look what you need to do with your open voltage. You need to increase the voltage to 1.2. So, who cares? Then your voltage open circuit voltage have to be 50 multiplied by 1.2. What's 50 multiplied by 1.2? I'm losing my mind here. 1.2 times 50 equals 60 volt. 60 volt. So actually, my friend, this voltage, this panel that's supposed to have 50 volt open, now when I size the conductors and when I do all my calculation, you're going to treat it as if it's a 60 volt DC, of course, DC system. So you have to adjust the voltage based on the temperature. Any question about this? Who cares though? Who cares? If you don't take this into consideration, you could end up at certain time in the winter in Minnesota exceeding the 600 volt, and your conductor that's supposed to only insulate for 600 volt, now you got into an 800 volt because the temperature went so down, and semiconductor equipment are working better and creating more voltage into your system. So long story short, the insulation might not be able to insulate the voltage, and you short and you ground fault. So pay attention to this table, guys, if you were to use it. Very important table. Easy to use based on the ambient temperature in the area and the open voltage of the system. Another thing that you guys have to pay attention, because these are on the roofs. Every time you put conductors in the roof, you have to derate because of the reflected heat and the ambient heat. So in 2000, so if you put your conduit, let's just say I will put them at 3.5. So I put a block here, 3-inch block, and I pulled my DC conductors in a conduit right here, right? And this was 3.5, 3.5, the distance from here to here. So that's 3.5, right? And then I have to add 22 degrees. So if my ambient temperature, like in Minnesota, say 90 degrees Fahrenheit, I need to add another 22. If it's on the roof, that will become 10, 1, 0,
40.
What did they say? 40?
Yeah.
Oh, Celsius. No, don't go Celsius, Chad. Don't go Celsius. We're Fahrenheit. We can't add Celsius to Fahrenheit. Like apple oranges here. 40, that will give you 130 degree Fahrenheit. Done. So you have to derate based on 150 degree Fahrenheit. That's not just for all conductors, guys, not for solar. But solar becomes a big deal because it is a big deal for solar because we're almost outside. And then adjustment for carrying conductor. If you carry more than 2, you have to adjust it too. And that's all what I have, guys, for the solar photovoltaic systems.
Does that apply to DC conductors
Yes.
as well?
DC, AC, everything. DC, AC. Absolutely. That's crucial because it's almost the AC. You're coming, the DC is coming. If you're coming down with a DC, most of the time, major system, they put the AC, they come down with the DC, with the AC, really. But it applies to AC or DC. Your inverters, guys, we talked about the inverters can go from 2 kW to 500 kW. I don't know if we missed any of these things. Ground fault protection, we talked about this one. Chris, did we miss anything? Okay, I have inverter ground fault label, bipolar system disconnect labels. There's a lot of labels that you have to label the disconnect as solar photovoltaic disconnect and so forth. Combiner boxes and so forth. I think we covered most of the stuff that I want to cover anyway. Voltages, the limitation, guys, 600 volt, most of the system that we do just because of conductors, but you can go higher than that. Unless you're dwelling. Dwelling, your limitation is up to 600 volt. Other commercial, we're doing commercial, you can go higher than that. But then if you go higher than 600, you get into a whole regulation for 600. So most of the systems are limited to 600 volt or less. Any question, guys, about that? Okay, that's about it. Thank you.